We finish up part 9. We've got the end of part 9 and the first part of part 9 to do. And then I'm thinking we're going to knock out part 10. And that just leaves part 11 for unit 4. So we'll see. It's going to be the usual in this class, which is basically before you, we're going to go on to unit 5 before you have your unit 4 exam. It's kind of what we do. So, but it seems like this stuff we really hit hard yesterday. Seems like so long ago, but it was just yesterday's lab. We were drawing Lewis structures. And I could ask you questions like what's the geometry and all that around the nitrogen atom, and you'd say 3 sigma bonds, 1 lone pair electron, so you're looking at 4. So of course that makes it sp3 orbital hybridized, structural geometry tetrahedral, and what's the bond angle? 109.5. Okay, so true story, and that, so you guys can fill those in, right? So true story, I used to say, well, that makes a great radio station, and there's no, the dial doesn't go up that high. So I know, drat. So what do you think about the next one? For the central atom, which is the carbon atom, what do you think its orbital hybridization is? I'm liking sp2. Yep. So what does that mean that its shape is? Tetrahedral. Yep. Oh, sorry. Oh, darn it. Oh, trigonoplanar. Oh, get out of there. sp2 trigonoplanar. Yep. Very good. So what's its bond angle? 120. Yep. Okay. What about this one? What do we think? You can take either the, let's go with the chlorine. So what do you think with regard to the chlorine? What sort of orbital hybridization do we have? I'm liking sp3. Yep. Because we have 1 sigma bond and 3 pairs of lone pair electrons. So structural geometry, tetrahedral. Yep. And there is no bond angle. Not applicable. But if you put 1 on 9.5, I could go with that. So on your test next Thursday, you're going to have a Lewis structure. You're going to draw some your own Lewis structure, so be able to do that, or 3 points apiece. And then you're going to have a Lewis structure already drawn for you. I'm going to ask you questions. See, this one says, what is the orbital hybridization and the structural geometry of these atoms? Okay, so kind of starting with this atom and kind of going counterclockwise, actually. So this first carbon, what is the orbital hybridization? sp3, I'm liking it. So what is the structural geometry? Tetrahedral, yep. sp3 tetrahedral. Now, I'm pretty sure we're skipping over to this nitrogen. So how many sigma bonds coming from that nitrogen? Only 1 sigma bond. How many pairs of lone pair electrons? 1. So you're at the row that has 2. So what's its orbital hybridization? sp, and so what's its shape? Linear. Very good. You got it. So what about this carbon atom here? How many sigma bonds? Sigma bonds? 3. 3 sigma bonds, no lone pair electrons, so you're looking at 3, so what's its orbital hybridization? sp2, yep, shape? Trigonoplanar, yep. And then the last one up here, oxygen, how many sigma bonds? Just 1 sigma bond, and how many pairs of lone pair electrons? 2. So what do you think about hybridization? sp2, the shape is also trigonoplanar. Yep. Very good. So the same structure, we could ask these questions, and I think I'm going with some same atoms and same not. To answer the bond angle, I usually answer the whole what's its orbital hybridization and go from there. So we're going to go from left to right, and we're going to look at these 3 bonds. This one you guys told me, I'm pretty sure you told me this carbon was sp3 and tetrahedral, so what would that bond angle be? It's tetrahedral, it's 109.5, yep. So this one, we didn't do this carbon, so how many sigma bonds? Just 3, yep. Sigma, sigma, sigma. On one of these is sigma, the other's pi. So what sort of orbital hybridization? Trigonoplanar, so what does that bond angle make it? 120. I mean, that's a good example of, you'll see this Lewis structure drawn, you're like, no, Mrs. Snipes, that's 90. I'd be like, no, the real deal is it's 120, okay? Okay, so we didn't do this carbon atom either. So in a triple bond, how many sigma bonds are there? Just 1 sigma bond in a triple bond. So 2 sigma bonds, no lone pair electrons. So what sort of hybridization? SP. So it's linear, and so what's the bond angle? 180. It's the hot dog shape. Yep. So that's how that works. And then I just have some, I don't have a whole lot to add. Well, either one of these carbons. So what sort of orbital hybridization has the carbon that gone? Like an sp2, yep. Structure geometry, trigonoplanar, bond angle, 120. So actually this was C2H4, so this is that. Yep, very good. And then this one is that, the C2H2. So what sort of orbital hybridization do we have for the carbon atom? Just sp, yep. And then structural geometry, linear, bond angle, 180. Okay, so you guys told me this was sp2, trigonoplanar. Can almost see the trigonoplanar. And I think I mentioned before, there is free rotation around the sigma bonds, but you can almost see it. You get a pi bond outside the sigma bond, and there's no free rotation. Actually, that has consequences to how this molecule plays with other molecules. Okay. So that's this one. We're gonna, here in a minute, we're gonna go back up to the top of part 9, and we're gonna talk about bond lengths. And you guys told me yesterday that when you guys made that double or that triple bond, it seemed like the atoms got closer together, and they do. PM stands for picometers. That's the bond length. Okay. So again, I'm trying to put it on the board so we're on the same page, but the homework for parts 7, 8, and 9 will all be due on Wednesday. Okay. So let's go back to the first part of this and see what we got. Oh, but I know, I was going to put on the board. For each part you get done early, you get 10 extra credit points. So I know it's all about gimmicks, right? I don't know. It's fun teaching. What I feel like is I can add points. I can't take any points away from what my syllabus says, but I can add points here and there. So anyway, so bond properties. And some of this stuff really, this makes sense. I like stuff that in science that you're like, oh, this makes sense. So we're back at the beginning of part 9. So can you guys, everybody find this slide? It should say bond properties, like the 3rd slide or something, part 9. Okay. So a triple bond is stronger than a double bond, and a double bond is stronger than a single bond. Now that's assuming that you're comparing apples to apples. That's assuming that the same 2 atoms are connected. Makes sense. Okay. And if you're talking about that primary and that secondary bond, which one's stronger? The primary bond. Yeah. Your meat and potatoes make you stronger than your pie. So, yep, that's the real deal of it. So here we have carbon atoms that are triply bonded, doubly bonded, and singly bonded. And this is the strongest. Now this is assuming that you're going to have to cut through the sigma and 2 pi bonds here, the sigma and pi bond here, and just the sigma bond here. So this would be the least amount of energy required to break those 2 carbon atoms apart. Okay, here we're looking at, instead of carbon to carbon, carbon to nitrogen, we can see the same trend. Carbon triple bond nitrogen, which you actually saw with your HCN when you drew that blue structure yesterday. That's the hardest to break compared to just a carbon single bond nitrogen. Makes sense, right? So here are some bond energies between a pair of atoms. Bond energies, think of it as potential energy, and then also think of it as the energy to be required to break them. Potential energy as they are formed, and required energy to break the two. Okay, so bond energies. These are given in kilojoules of energy per mole of that bond. All right, bond lengths. Triple bond is shorter than a double bond is shorter than a single. Okay? Again, that's assuming that you have the same atoms that are connected together. There's another trend with regard to the distance between the nuclei of the atoms that are connected, and it looks like this. If you're talking about the same type of bond, that would be single bond or double bond or triple bond. The bond length will increase as the size of the atom increases. This kind of makes a little sense too. I'll buy that. So I don't know, we talked about atomic size in this mess of stuff. Was it just this unit? We said atomic size obviously increases as you go down, but if you're in the same period, it's backwards. Atomic size increases from right back to left again. So as the atomic size gets bigger, so does the distance. There is in the bond as similar, if you have the same type of bond. Okay. So, same atoms bonded together. The shortest is the triple bond, the longest is the single bond. Triple bond shortest, single bond longest. And this is kind of showing you kind of the potential energy going to then ultimately be associated with the energy as the two atoms are bonded together. This is as they're bonded together, and this is as they're separated. So lots of potential energy separated here. Potential energy separated. Here, this is actually then energy associated with the bond. This diagram confuses. All right, so bond length, bond energy. Single, double, triple. Bond length decreases, bond energy increases. Okay, here we have carbon, nitrogen. Again, single, double, triple. Bond length decreases, bond energy increases. And here we have carbon, oxygen, single, double, triple. Bond length decreases, bond energy increases. It's just kind of another miscellaneous table. And I did, let's see. No, I was going to try to pick out, this is carbon. If we wanted to look at the trend of carbon being, for instance, singly bonded to we got nitrogen, we got time. So here we have carbon, single bond carbon. Oh no, my pen stopped working. Okay, carbon, single bond carbon, 154, carbon, single bond nitrogen, 147, carbon, single bond oxygen, 143. Let's find carbon, nitrogen, and oxygen on the periodic table. So carbon, nitrogen, and oxygen. And let's double check which of these is the largest. Carbon is largest. So if it's the largest, it should have the longest bond. Let's see if it does. We have bond lengths up here, so you're looking at 154 versus 147 versus 143. So that's kind of what we're talking about.
What power is PM?
The picometers, pico is 1 billionth, I want to say. Yeah, very short. Short. Okay. No. Okay. Now we're going on to part 10. So we should have bumped up against hybridization there. Jumping around, jumping around. So, Lewis structures. Actually, I'm just going to kind of talk you through again what you guys did yesterday. What you did was you came up with a pot of valence electrons. We're going to do an example here with the formate ion. And then I'm going to kind of show you something from the formate ion called resonance structures. Pot of valence electrons, you arrange them. What atom goes in the middle? Lowest electronegativity. Yep. Does hydrogen ever go in the middle? No. Okay. Yep. You arranged them. You drew the single bonds. That was step 2 and 3. Okay. Then you did like a little subtraction. Your pot of valence electrons minus the ones that you used for sigma bonds. You came up with what was left over, and you put them around your terminal atoms. You made your terminal atoms a complete octet. That's step 4, I think. And then step 5 was you actually swang, if required, from lone pair electrons to form a pi bond if needed. So I want to talk about this last step just a little bit more. Okay. So the example we're going to take is the formate ion, HCO2 with a -1 charge. So here's the pot of valence electrons like you did yesterday. We have 18 to distribute. You would put carbon in the middle because carbon's a lower electronegativity than oxygen. Hydrogen never wants to be in the middle. The Lewis structures on your test will be this sort of approach. They won't be where you have more than one central atom. Okay. So we have 6 electrons there. 18 minus 6 is 12. So we're going to satisfy our terminal atoms first. Hydrogen's done, but we need to make oxygen happy. They only had 2 there, so they need 6 more. That's 3 pairs. So I put 6 here and 6 here, and I've used my whole pot. Okay, so this is where step number 5 actually applies. We're going to have to swing lone pair electrons in. Now, the whole point of resonance structures goes something like this. I could swing them from this oxygen, or I could swing them from this oxygen. Okay. We can actually, using different isotopic forms of oxygen, we can tag those and know which is going from which. You might be like, oh, they're the same. No. Matter is not the same as other matter. Okay. So in this case, you can see I did the swinging from my north oxygen. Would it have to be that way? No, not necessarily. But this would be one possibility. Now, if you guys swang from the east oxygen, would be right. Oh yeah. Okay. Notice, yeah. I think that's the biggest thing I want to say. So the whole idea of resonance structures just goes into when you're drawing your Lewis structure, that last little bit where you are taking some lone pair electrons, swinging them in so they do double duty, that they'll be possessed now, there'll be a pi bond, 2 electrons that forms a pi bond between 2 atoms. And so now they are continue to be custody of the atom they came from, and now they're shared with the other atom. Okay. So this was the one that we came up with a minute ago, but honestly, these 2 structures are what it really is. So formate actually does both of these. That double arrow, I don't know if you remember, and I brought it here today. Okay, here is my benzene. And the other day, Wednesday, I drew the structure of a benzene, 6 carbons that alternate single, double, single, double, single bond. I had one extra bond there, but you know what I mean. Okay? And I did this double arrow, meaning it kind of goes back and forth. In General Chemistry 1, we basically stick with one-way arrows. Arrows, of course, pointing from left to right. And in General Chemistry 2, we're going to kind of be talking more about, there's a lot of things that kind of go back and forth. Life's a little more complicated than we wish it was sometimes. Not only this, but let's take a look. It's a subtle thing, but can you see, I've lost the brackets, which I guess that's okay. But can you see where I've gone ahead and shown the oxygen atom that keeps its 6 electrons, 3 pairs of lone pair electrons, is going to actually carry a partially negative charge. Partially negative charge. The other resonance. So I think this is kind of weird too. So if we kind of think of those 2 possible resonance structures of formate as being something kind of out there, something that isn't real, okay? And then what is real is kind of it's not a hybrid, but it's kind of a mixture of the 2. It kind of goes back and forth between me and the 2. The other day, when I was talking about benzene, when I think of something that has possible resonance structures like benzene or formate, the word resonance structure makes me think of resonate, and that's what you do. You take your finger and get it wet and put it on a glass, and it kind of makes that sound. So here's the formate ion, and you can kind of see the central carbon atom, sigma bond hydrogen, and you can kind of see that pi bond kind of flipping back and forth between these 2 oxygens. Okay. So, things that have a resonance structure or a pair of resonance structures, like formate, okay, can go back and forth, and it really is something kind of in between the 2, or benzene, they carry with them an extra coolness. They're extra stable. Oh, by the way, this word I like this word in chemistry. It's called electron delocalization. So kind of this to me looks like totally we have electrons delocalized outside of the sigma bonds. We have 3 pairs of electrons that are participating in pi bonds outside of that ring structure. I think that is so cool. And formate ion does that too. Electron delocalization. Well, when you draw Lewis structure, sometimes you come to a turning point, like you guys did with your, I can't remember what structure you guys had yesterday, but you could have swung from your chlorine or you could have swung from your oxygen atom. I saw all of you guys swing from your oxygen atom because it made more sense. Okay, so sometimes but if you had swung from your chlorine atom, that would have been, you could have given everything a complete octet that way too, but it wouldn't have made as much sense what you know about expected valence. Your final Lewis structure, if there is some sort of partially negative, partially positive, it should make sense. So for instance, in the formate ion a minute ago, I kind of showed you the partial negative on the oxygen. You're like, well, does oxygen want to be partially negative? You're like, I can see it wanting to be. Its electronegativity is pretty high. So that makes sense. Your final Lewis structure, the one that makes sense, will be the one that has, I'm not sure what that's after. We talked about using the expected valence for an atom. Okay, most people get this right. So carbon dioxide, you could come up with a pot of valence electrons, and these are a pair of Lewis structures. I'm going to show you 2 Lewis structures that really make sense for carbon dioxide. So if we call this first one A, the one on the left A, and the one on the right B, how many people think that A looks like the best Lewis structure? Most people do. And we probably think that right away, even if we didn't know anything about chemistry, just because it's so much more symmetrical. But let's look at it in light of the thing that you ran into yesterday. What's the expected valence of an oxygen atom? 2. Yep. So here we have it reaching out twice, and then over here we have it reaching out 3 times in one time. So this is a disfavored resonance structure. Same pot of valence electrons, but I would say this is not very likely. Sometimes you'll run into possible structures that aren't very likely, but actually participate, and they are a player to a certain extent. So one of the things I want to be able to do now with Lewis structures is to point at an atom in a Lewis structure and to say that atom has this formal charge. And you'd be like, you know, when we talk about charges, we think of ions. Okay, and here I'm going to make us think of something called formal charges on a neutral molecule for each atom. So formal charges are the apparent charge that is associated with an atom at what's called the nonpolar limit. Nonpolar limit, right? What is the nonpolar limit? So we know that, let's put it this way. Well, remember we talked about nonpolar covalent bonds? Covalent bonds where electrons are shared. If they're shared more by one atom than the other one, then there's a degree of polarity. So we have partially negative and partially positive. If it's nonpolar, that means that actually the tug of war is totally equal. So nonpolar, think of that. Limiting situation when the covalent bond is thought to be totally covalent or nonpolar. So we're going to play a little game. Anytime we see a dash, which is a covalent bond, we're going to think, we're not going to look at, well, which one's more electronegative. We're just going to simply say, we're going to split the custody. We're going to give one of those electrons that makes that covalent bond to this atom, one of those electrons to this atom. That's the game. Oh, and then also, if an atom in a Lewis structure has a dot, pair of lone pair electrons, it gets to keep those lone pair electrons. It seems only right, doesn't it? So, I mean, it makes sense. It's going to be easier to show you. So once we have that figured out from the Lewis structure, okay, we do a little subtraction. And the subtraction goes like this. For each atom, this is how you calculate the formal charge. You look at the periodic table. If you want to, on top of this, write periodic table, you can't because my little pen's not working again, which I am so disappointed. So you'll look at the periodic table with the valence, number of valence electrons for that atom. And then from that, you will subtract on your Lewis structure, what you came up with is the number of valence electrons at the what's called the nonpolar limit. You do that little subtraction, and whatever that number gives you, that's the formal charge. That's it. Okay? So again, it's easier to show you than to talk about it. So let's see. Oh, I'm going to show you here in a minute. What else we got? So formal charges. If you're dealing with a neutral molecule, preferably the formal charges of your atoms are going to be 0. But if they aren't 0, then if you have a +2 formal charge, you better have a -2 formal charge somewhere in there so that the whole thing kind of makes what we call neutral for the molecule. The closer to 0 your formal charges, the better it is. Actually, we're going to revisit carbon dioxide here in a minute and look at the formal charges of those 3 atoms, those 2 possible resonance structures. If you do have a negative formal charge, then it should be on something that's pretty electronegative. Okay, if you have a positive formal charge, it should be on probably one of your metals or something that has a low electronegativity. If we're dealing with a polyatomic ion, then if you add up all the formal charges, it shouldn't be 0. If you're dealing with a polyatomic ion, then if you add up all the formal charges of the atoms there, it shouldn't be equal to the charge of the polyatomic ion. It's like counting beans. That's what it feels like. So, remember, this is kind of a little game we're playing, this whole idea of at the nonpolar limit, but it can kind of tell you where your regions of partial negativity and partial positiveness might be in the molecule. Finally, oh my gosh. So here's a correct Lewis structure, and we're going to come up, let's see what we have, 5 atoms here, and we're going to come up with a formal charge for each of those 5 atoms. Okay. So what is, what my fields look like? Okay. So you guys can go back and forth. Before I go on to the next one, do you guys already have Yeah, good. So can you see on the next one that I'm going to go ahead and break this, and I'm going to give that one electron and this one electron from this. For this oxygen atom, I'm going to break it right here. It's going to get one of those electrons. One electron's going to go here. This, I'm going to break it, kick one electron up, one electron down to nitrogen. Here you would probably tell me there's 4 electrons there. I'm going to break that and give that guy 2, nitrogen 2, and give the oxygen 2. Okay? So that's going to be the number of electrons at the nonpolar limit. And it kind of looks like this. Okay, so kind of these little circles, whatever in the circle for that atom is the number of electrons at the nonpolar limit. So that's going to be the number that what we subtract from their valence electrons. So how many valence electrons for, look at the periodic table, how many valence electrons for hydrogen? Not your question. 1, yeah. So we take 1 minus 1, and we get 0. I know, it's kind of anticlimactic. 1 minus 1 is 0. So its formal charge is 0. I think I do the next oxygen. So what is the number of valence electrons around an oxygen atom? I'm liking 6. And then how many electrons do we have at the nonpolar limit? 6. So 6 minus 6 is 0. Now that's not unusual. If you come up with formal charges of all the atoms are 0, that's fine. It just means it's probably the correct Lewis structure. I think I go over, I can't remember what I go to next. Yep, I go over to this oxygen atom. So for this oxygen atom, it's the same, isn't it? So I'm going to take 6, the valence electrons, minus 6, which is the number of electrons at the nonpolar limit. I get 0 there. Now, I can't remember. Yep. So now, what about this oxygen up here? The first number is going to be the same because it's 6 valence electrons, but how many electrons does it have at the nonpolar limit? 7, and this is where it gets exciting. So what's 6 minus 7? Negative 1. So finally, we have a non-zero number here for the formal charge. Let's see, nitrogen, how many valence electrons? I'm liking 5. So what are we going to subtract from 5? 4. So what's 5 minus 4? 1, or plus 1. And then you can see on my answer key, I didn't put just 1, I put plus 1 to kind of emphasize its side of 0 it's on. Yay! Right? It's a neutral molecule. We should expect then that if we add up all the formal charges, it's equal to 0. Is that the case? Yep. Does it seem right that oxygen's more electronegative than nitrogen, so we have partial negative on oxygen? Yep. Looks good to me. Okay. That's formal charges. So on your test, I'll ask you something about formal charges. And this one we'll also be doing Wednesday. So let's go back and look at those 2 resonance structures of carbon dioxide. And you guys told me that this one makes more sense, expected valence and all that. But let's take these 3 atoms and knock out, you probably already have it written down there. Let's knock out the formal charges of the atoms. So what about this oxygen atom? What is the number of valence electrons for an oxygen atom? Just 6. At the nonpolar limit, how many electrons do we have? Yeah, I get 6 also. Yep, so 6 minus 6 is 0. So you put 6 minus 6 is equal to 0. But it was kind of confusing. So does it seem like if you did the little thought process, it'd be the same over here? I'm liking 6 minus 6 equals 0. What about that carbon atom? How many valence electrons for a carbon atom? So the group 4, yep. So 4 minus, how many electrons does it have here? 4, yeah, 4 minus 4, that's also equal to 0. So let's go over here. Now here are, it's going to change it up a little bit. What about this oxygen atom? What's the first number that you're going to subtract from this oxygen atom? It's simply 6 again. So here I would put 6 minus, but then how many electrons at the nonpolar limit. 2, 4, 6. I get 7 also. Yes, thank you. So 6 minus 7, right? -1. How about over here? 6 minus... I can't think. Yeah, I'm thinking 5 also. Yep. So here we get 6 minus 5 or +1. So we had a -1 and a +1, right? What about the carbon? So it's 4 minus 4, yeah. Yep, so the carbon in both cases, the formal charge is 0. Yep. So the formal charge is 0 here. We have 0, 0, but over here we have a -1 and a +1. Yep. Okay, so here is the deal, and I'm making up as I go, right? So, you gave me 6, right? So we still have part 7, which we talked about, part 8, which we didn't, but it's just like your lab. So, and part 9, which we finished today. And so this is the sheet. This is why I was like, are you serious? I've been putting it off too long. So 7, 8, 9, you're like, well, there's just a few problems with they have all these multiple parts with them. And it'll be good for us to do, but I'm not going to get it done before I go home today. So 7, 8, and 9, and then we just now finished 10. 11 won't take very long at all. We'll knock that out Monday before we start on Unit 5. So these will be due Wednesday, okay, they'll be due Wednesday the 6th. But, okay, so that's 40 points there. That's a lot of points. Okay. If you turn them in, anything turned in money Monday, and you earn double. Now these points would only be good for your assignment points. And I think that I thought about it, but unless somebody convinces me otherwise, which I'm convincible. But remember you had the lab EC for extra credit. I'm still not going to make that due. Do you want me to make that due Wednesday, or are you going to leave it Monday? It's very hard. Who wants it to be extended out to Wednesday? Okay. We'll make that due Wednesday. Or, oh, you turn it in early, you get double due Wednesday, or early equals double. Oh my gosh. Sounds so complicated, but okay. Very good. So everybody have a good weekend. Looks like it's going to be chemistry sort of weekend.